Assalamu alaikum.
Walaikum salam.
Okay, so welcome to the lecture 9 of signals and systems. Okay, so just to recapture what we have done so far in our previous two lectures. So our topic is related to what we call as Fourier series. And we have found that any periodic signal in discrete time will always have Fourier series representation. Whereas for continuous time periodic signals, we can say that all practical realizable signals will have Fourier series. So for continuous time periodic signals, the two equations that are part of Fourier series are, so if x of t is a continuous time periodic signal, we can make use of this equation, which is known as synthesis equation. And with the help of this equation, we can represent essentially all periodic continuous time signals. In this particular equation, the important point is how we will find out the values of these Fourier series coefficients, or also known by the name of spectral coefficients. So we also derive this equation. So with the help of this equation, which is also known as analysis equation, we can find out the corresponding Fourier series coefficient for this signal. Similarly, for discrete time periodic signals, we have this analysis equation. And this synthesis equation. In this case, omega naught can also be written in terms of fundamental period t, whereas in this case, omega naught can also be written in terms of fundamental period capital. This is something which we have already covered. Now let's find out what is the use of this representation for LTI systems, which are focus of this whole course. What advantage we can take from Fourier series representation if we are analyzing an LTI system. So Fourier series and LTI systems. So what we have already covered is that if there is an LTI system, and if the input to this system is an exponential signal of this form, e to the power j omega t, then the output of the LTI system for this type of input is very simple. It will be the same signal multiplied with a factor, and that factor is known as eigenvalue from mathematical point of view, and from signal and system perspective, we call it frequency response. So what is this function? Mathematically, we call it eigenvalue, and in signal and system language, we will call it frequency response of the system. And we also found that this function, eigenvalue, is equal to this integral here. So if you want to calculate this eigenvalue or frequency response, you can make use of this equation, which we have already covered in our previous lectures. Similarly, for discrete time LTI systems, so now if the LTI system is discrete, and again, if we apply input like this, e to the power j omega n, for this input, the output of the LTI system is very simple. It is the same input multiplied with a function that I'm going to represent in this form. Again, this particular function is eigenvalue, or you can call it frequency response of LTI system. And if I want to find out what is the value of this function, we can calculate it with the help of this equation. So this is the importance of this is the importance of function that is used in Fourier series. So if you look at this function, and then if you look at the Fourier series, in continuous case, the signal is represented in the form of this function. Similarly, for discrete time, the given input is represented in terms of this function. So based on this, now we can say that if the input of the LTI system, so now the same LTI system, and if its input, which is generally represented by this notation, and if we assume that this input is a continuous time signal, then we can always represent it in Fourier series. So this signal, if it is periodic, we can always represent it in this form. Now, what is going to be the output of our system to this input? Because this system is linear, so it will satisfy the principle of superposition. So if input is a linear combination of exponential signals, output will also be the linear combination of exponential signals. Also, because the output will be changed. So if input is this, output is this, but there is also one factor. And the value of this factor depends upon the frequency. So over here, the frequency was omega. So that is the reason this function h is dependent on omega. So in the same manner, I will say what is going to be the output? Output will be the same linear combination. So again, we will take summation from minus infinity plus infinity. We will have the same signal. So there will be e to the power j omega naught t, this one. But what will happen to ak. This ak will get multiplied with the eigenvalue of the system. So what is going to be the eigenvalue? Eigenvalue will be the function of k. Sorry, let me write it. It will be the function of k omega. So what we can say about this behavior is that when a signal of this form, when it passes through LTI system, what does this system does to this signal? It changes the Fourier coefficient. So the input Fourier coefficients are ak, and output Fourier coefficients will be ak multiplied by this factor, which is the frequency response of the system. What is h of j omega? H of j omega is the frequency response of the system. So we will say ak are Fourier series coefficients of the input x of t. And I will say ak multiplied with frequency response at k omega naught are Fourier series coefficients of the output y of t. So input fundamental frequency is omega naught. Output fundamental frequency will also be omega. But what happens to the signal? For input, Fourier coefficients are ak, but what will be the Fourier coefficients of output? That will depend on this function. That will depend on this function. So we can describe the behavior of LTI system as if this system is going to modify the Fourier series coefficients of the input signal. So depending upon what is the value of h, the Fourier coefficients can increase or can decrease. In a similar manner, I can describe the behavior of discrete time LTI system. So now if this is a discrete time LTI system, and if the input of this system is x of n, and if we assume that this input is a periodic signal, then we can always represent periodic discrete time signal in this form. Now, if such type of input is given to an LTI system, what will be the output of the system? So using the principle of superposition, because system is linear, we can say that output will also be the linear combination of the same signal which was applied as input, but this system is going to multiply the Fourier coefficients ak with a function that we call as frequency response, and the value of that frequency response will be function of k times omega. So all this LTI system is doing is it is changing the or modifying the Fourier coefficients of input, and the Fourier coefficients of output are now ak multiplied with this function. So these are Fourier series of input, and these are Fourier series coefficients of output. So one thing that you need to keep in your mind is that whenever you are dealing with LTI system, this LTI system in continuous time is characterized by its impulse response, which we represent as h of t. And now we have introduced another property of LTI system, which I am calling as frequency response of LTI system. But you can see that this particular frequency response, which I'm representing as with this symbol, you can clearly see that this response is related to impulse response. So frequency response, what will be the frequency response of this system? It is totally dependent on what is the impulse response of this system. But impulse response is a function of time, and frequency response is a function of omega. That is one important difference, or you can say frequency response help us to transform a time domain property, which is impulse response, into frequency response. And in order to perform this transformation, you have to make use of this integral. In a similar manner, when you are dealing with a discrete time LTI system, so in time domain, this system is completely characterized by its impulse response, which is h of n. But this time domain characteristic of the system, it is now represented in a different form, that is this one, which is again frequency response. But you can see this parameter, which we are calling as frequency response. How to calculate frequency response? You have to make use of this equation, which is summation. But you can clearly see that this, what is going to be the result of this summation, it is dependent on h of k. When what is h of k? H of k is the impulse response of the system. So this is something that you need to keep in your mind. Now let's solve one example to apply the concept that we have developed after going through this topic. Let's assume that there is an LTI system and its impulse response is given to you. It is impulse response is e raised to power minus t u of t. This is the impulse response of the system. And let's assume that the input that is given to this system. So let me draw the block diagram of the system. So this system is given to us, it's LTI system, and its impulse response is given to us, e power minus t u of t. The input that is given to this system is represented in a Fourier series representation, ak e raised to power jk 2 pi t such that k is from -3 plus 3. And we are also given information about Fourier coefficients. So a naught is equal to 1, a1 and a minus 1 is also given. It is 1 by 4. A2 and a minus 2 are equal, and they are also given to us 1 by 2. And a3 and a minus 3 are also given to us, and they are equal to 1 by 3. So with this information, we are asked to find out what is going to be the output of the system. So now we can apply the Fourier series tool that we have developed, because input to this LTI system is represented in Fourier series. So based on the discussion we had, we know that output will also be a signal like this multiplied with a particular function that we call as frequency response. So if I want to represent the output, I can say that output can be generally represented as AK h of function of k omega naught e raised to power jk 2 pi. Also, you can see that this 2 pi means that omega naught is equal to 2 pi. Omega naught is equal to 2 pi. So now, based on that, I can say that this omega naught for this particular example is equal to 2 pi. So all I need to do is, these coefficients are given to us, but I need to find out this function. Once I know this function, then I will be able to find out the Fourier coefficients of this. So I can, let me call these Fourier coefficients as bk. So bk are the Fourier coefficients of output, and bk is equal to ak multiplied with this function. So first of all, we need to find out this function. So what is the general form of this function? If you go back, how to find out the frequency response? This is the equation that we need to use. H of j omega is equal to this. And then later on, we will substitute the value of omega. So first of all, I will find out H of j omega. So it's equal to minus infinity to plus infinity h of tau e to the power minus j omega tau d. Now we are given frequency response, impulse response. So I can replace over here, and because of the nature of the frequency response, because there is a unit step function, so it means this function exists only between 0 to infinity. So this can help us to change the limits. So rather than from minus infinity to plus infinity, the non-zero result will be from 0 to plus infinity. And within this interval, the value of the function is e raised to power minus tau. And of course, this function is equal to 1, and then e raised to power minus j omega tau. So you can easily find the answer of this integral. So you could say, well, let's say minus tau can be taken as common, and then you have 1 plus j omega. So if you solve this simple integral, what you will get, h of j omega will be equal to 1 divided by 1 plus j omega. Now, in order to find out different values, so if I expand this, it's obvious that I need to find out. So let me expand this, okay, so that you can get the idea. So what is going to be the output? The output will be equal to, let's say, let me take the value of, let me take the -3 value. Let's -3 से start कर. So what we will get, a -3 and h of -j3 2 pi. Then you will have a -2 and h of -j2 of 2 pi. Then you have a of -1 then you will have a of 0, and of course this will be 0. So this is how you will find. But what is the value of this coefficient? So all you need to do is put the values of omega over here. Okay. So if I want to find out, let's say b of -3, इस फॉर्म अगर b of -3 है, इस कोफिशिएंट को हम क्या नाम दे सकते हैं, b of -3. तो b of -3 किसके बराबर होगा, a -3. a -3 किसके बराबर है, 1/3. तो आप लिखेंगे 1/3. And then what is the value of this function for this value? ठीक है. So it will be 1 divided by 1. तो मैं यहाँ पे लिख लेता हूँ so that you get the idea कि ओमेगा को मैं रिप्लेस कर देता हूँ k ओमेगा नॉट. तो ये हो जाएगा 1 + j k ओमेगा नॉट हो जाएगा. ओमेगा नॉट की वैल्यू ऑलरेडी हमें पता है, इट इज इक्वल टू 2 पाई. तो यहाँ पे हो जाएगा 2 पाई. तो इन ऑर्डर टू फाइंड आउट b -3, यहाँ पे हम क्या पुट करेंगे, k की जगह हम क्या पुट करेंगे, -3. तो आपके पास क्या आ जाएगा, 1 - j 6 पाई. ठीक. सिमिलरली इस कोफिशिएंट की वैल्यू अगर मैं फाइंड करना चाह रहा हूँ, इसको आप कह दें b -2 कह दें. So what is b -2? It is a -2 is equal to 1/2. 1/2. और इसको हम किस फैक्टर के साथ मल्टीप्लाई करेंगे, यहाँ पे k की जगह आप -2 पुट करेंगे. तो क्या जाएगा, 1 divided by 1 - j 4 pi. So this is, I think, simple enough. बाकी आप इसको खुद कर लेंगे अगर आप इसको b1 - 1 कह देंगे. So you can see that जो आउटपुट है, इसके जो कोफिशिएंट्स हैं, उनको फाइंड करने के लिए पहले हमें फ्रीक्वेंसी रिस्पांस को फाइंड करना है और फिर उसको डिफरेंट k की वैल्यूज के लिए हम करते जाएंगे. तो अकॉर्डिंगली ये a0 से हमारे पास b0 आएगा, a1 और b -1 से b1 और b -1 आ जाएगा, b2 b -2 हम इसे निकाल देंगे और इसी तरीके से b3 और b -3 निकाल. ठीक. So these are all coefficients of, अगेन यहाँ पे मैंने इसको h of t लिखा हुआ, h of t के साथ ये फैक्टर भी. ठीक है, ये मैंने नहीं लिखा हुआ. So with every function यहाँ पे आपके पास एक्सपोनेंशियल टर्म. ठीक. एनी क्वेश्चन?
एक्सक्यूज मी सर.
जी बोलें.
सर जी इस क्वेश्चन में ये a0 a1 ये दिया है या हम इसको फाइंड करेंगे?
गिवन, ये गिवन.
सर जी क्वेश्चन में दिया होगा या अगर क्वेश्चन एग्जाम में हो इस तरह तो ये दिया होगा ये एग्जाम में?
So you are given this information and you are given this information and you are asked to find ये फाइंड कर. ठीक है. इसके बगैर तो आप आउटपुट फाइंड ही नहीं कर सकते ना। क्लियर है?
Yes, sir, clear.
Yes, sir.
Okay. Any other question? Okay, let's move on to next topic, which is related to filtering. So in many electrical systems, we come across a situation where we have to design a system that can change the relative amplitude of different frequency components present in the signal. And the circuit or the system that we use for such purposes so that we can pass certain frequencies and block certain frequency is called filter system. So let's look at the Fourier series and then behavior of LTI system in terms of filtering behavior. So LTI system को हम अगर as a filter अगर use करना चाहें, so वो किस किस्म का filter होगा और filter की कौन-कौन सी standard types हैं. So this is what we want to cover in this particular topic. So what we are going to do is we are going to divide the filtering system into two categories. Okay. We are going to talk about frequency shaping filters, and the other type of filter that we will talk about is frequency selective filters. So these are two categories of the filters that I want to discuss over here. What is the difference? There is a small difference in the behavior of these filters. So let's talk about वो क्या फर्क. In case of frequency shaping filter, we don't want to completely block frequency components. We just want to change the relative amplitude of different frequency components. So these filters change the shape of the spectrum of the signal. Whereas frequency selective filters are those filters which pass some frequencies and block certain frequencies. So these filters pass some frequencies essentially undistorted. It means they are not going to disturb these frequencies, and significantly attenuate or eliminate other So the difference is obvious. In case of frequency shaping filters, we don't want to attenuate completely any frequency. We just want to change the relative amplitude. When you change the relative amplitude of different frequencies, so as a result, what will happen? The shape of the spectrum will change, which we are going to talk about in detail in a short while. और जब frequency selective filters की जब हम बात करते हैं, these are such kind of filters जिनका purpose ये होता है कि आप कुछ frequencies को as it is pass करना चाहते हैं, but you want to attenuate or maybe completely eliminate some other frequencies. तो फिर उसको हम frequency selective का नाम. So with this definition of these two filters, let's look at the examples of LTI systems जिनको हम as a filter use कर सकते हैं, और we will also talk about कि frequency shaping filter को हम कहाँ use करते हैं और frequency selective filters को कहाँ use करते हैं. Let's talk about them in the next session.